would also be grateful if you could, sign up just to keep track of who decided to come. And I'd like to thank everybody for being here. I know that it's going to be a long day for some of you because many of you are coming from far. And I'm very pleased to know that there is a very large representative from the industry today. So thank you very much for being here. I'm going to give immediately the throne to Patrick Naylor, who's going to give a presentation on introductory presentation on space-time processing in audio applications. So here he is.
Thank you, Augusto. So, yes, it's a great pleasure to come to Milan this morning. A little bit cold, but fresh, and it's always nice to visit to Italy. So my topic will be broken down into some different sections. First of all, I'll talk about the characteristics of signals and the environments in which we wish to do this processing. And then I'll talk about the tasks that we would like to perform and the objectives of those tasks. And then I'll try to paint a picture of how we might try to do space-time processing, what are the paradigms that we will use in this context. And then I will give some examples of the approaches which we will use in signal processing to implement the tasks above. Then I'll look at some more targeted applications. How can we apply the signal processing in the direction towards industrialization and commercialization of this technology for the future? And after some conclusions. I asked myself, why am I personally interested in audio and acoustic signal processing? And ever since I was this big, I always had a passion for audio and acoustics and a great interest in sound and also music. And I realized that I have an interest in the way in which humans process sound. It's quite amazing what can be done. I gave a picture here. This is the British Prime Minister so far, still. In this conversation, there are many signal processing tasks happening. It's an interactive communication, sometimes with also visual stimulus of lip reading, etc. It's in a noisy environment. There could be more than one person is talking at the same time, and supported by gesticulation with the hands. It's a complicated process, but the communication is very close to 100% intelligible. And the functions which are going on in the human being include many diverse things, including hearing and talking, interactive communication. But we can also think of entertainment applications where we want to have an immersive experience of an entertainment like a movie and so on and so forth. So in human beings, we can also think that we are executing algorithms with two sensors in an everyday space, in this room or in an office or whatever. We can detect sounds, we can do localization and tracking of sounds, many other things. And this is my motivation. So I would like to try to achieve at least a human performance, and maybe even a superhuman performance in speech, audio, and acoustic signal processing. And for that, I want to aim to have an immersive experience, and I know for sure that I can't do it with only one sensor or one rendering device. It means I need to use something multi-channel. So if we go to the textbooks now for audio and acoustics, we can try to find out what is the state of the art, and we can also put our intuition, our experience of engineering, and we will see that we want to consider multi-channel signals which can be rendered for playback and also captured for sensing. The acoustic waves will propagate in a space. It could be a complicated space, with reflections, reverberation, noise, etc. And that at any point in the space, the signal will be varying with time. So we have this concept of signals varying in time and in space as we move around the environment. And the space cannot be ignored. So we always will render sound within some acoustic environment. And of course, I mentioned already reverberation and noise. And we can really say that the textbooks do not give us enough information to handle this problem. We're really at the stage of science where we will soon be able to write some textbooks, but yet the things which we can read are only very much at the beginning of their life, nascent technologies, so emerging technologies in this area. So, what do we mean by space-time? So I give this definition here, which is space-time processing involves any mathematical model that combines space and time into, well, combines them into a single continuum when we think about the dimensions of space and the dimensions of time at the same time. And the tasks can be broadly expressed in two boxes. On the left-hand side, the idea of rendering, which means that we want to control the sound field at over some spatial dimension. We will have a loudspeaker system which will render the sound in a controlled way. In the right-hand side, we have the idea of sensing. So we would like to be able to control the spatial sensitivity of a sensor. And that's about controlling the directivity pattern. So we don't think anymore about omnidirectional microphones or omnidirectional loudspeakers. We think about the sound field in the spatial orientation. And that tells us that for realizing these systems, we need to move from single sensor to multi-sensor. And this could be over a wide range of applications. I spend many hours trying to persuade mobile phone manufacturers to have more than one microphone. And even to have two microphones is a huge step for them in terms of the cost and applications. Also with loudspeakers, most people are familiar to have two loudspeakers, less familiar to have 20 or 200 loudspeakers. So where does this technology lead and how does it fit into our daily life in an acceptable and economic way? These are some of the important questions. But they're not new questions. Even in the 1960s, people were already doing space-time processing. But in a rather simple way, I have an interest in line source loudspeakers. And I found some old papers. This is from 1993. So I was alive at this time, but quite young. Sorry, 1963, thank you. This is many years old. Trying to achieve a constant directivity pattern from a line source loudspeaker. And they use some very, we would say now, simple approaches using analog filters and loudspeakers, a low frequency array, a high frequency array, and different filters to achieve a directivity pattern. So this topic is not really new, but I would say the advancement has been limited, possibly because of our mathematical ability, possibly because of our technological capability, but now we see some breakthroughs. We start to see some emerging technologies which could lead to applications in the near future. These things are mostly for churches and halls, auditoriums in those days. So let's come up to date now to the current perspectives. And the first perspective would be of wave field analysis and rendering. So instead of a simple loudspeaker array, we may consider a circle of loudspeakers whose job is to control the wave field within the circle, where the sound pressure is controlled over some spatial dimension Q and some time T, and can be sensed also using a circular microphone array such that we sense the wave field on a 360 degrees visibility on a plane. So we move from 1963 to maybe 2011, even 2008 or 9, this technology is already available, to have a support of mathematical notation and the support of practical demonstrations coming together to advance the capability of this technology. As well as moving in a plane, we can also consider 3 dimensions when we move from circular to spherical coordinates. So there are some products now. This is the Eigen mic by MH Acoustics, which can sense in 360 degrees in azimuth and also in elevation. So we can control or sense sound fields in 3D. The second approach here would be called point-to-point analysis, where we consider in a room we may have a sound source located at a point in space and perhaps an array of microphones located on the wall. And our job is to try to analyze the point-to-point propagation of the sound from the source to the multiple sensors. And we can build signal processing systems which model this. We have a source, we have an acoustic channel, we have some microphones, some processing, and we extract a signal which contains better and more information than only the microphone signals. We can also do it for more than one source if we have multiple sources in the room. So the signal processing models are being built and exploited to model practical room acoustic environments. And the impulse response of the acoustic impulse response of the rooms looks typically something like this, with a direct path and many reflections occurring because of reflections from the walls, first order, second order, and so on and so forth. The third approach might be based on geometry, where we have a source in a room here and a receiver in another, perhaps in another room or in another position, and we're interested in which of the waves leaving the source actually arrive at the receiver. And by exploiting some ideas of computer vision illumination, one can consider tracing rays or beams to understand better how the sound propagates from the source to the receiver. So now let's think about the design of algorithms, signal processing algorithms that might exploit these paradigms. And I asked the question here, what can we measure, what can we sense, what can we touch in this domain? And I get the blackboard out in my office and try to draw some things to brainstorm this idea. And we can come up with some different things. Some are the obvious ones. We can work in the time domain, or we can also work in the frequency domain, and we can introduce spatial coordinates. So time, space, but equally frequency can be used in spatial processing as well. We can think of some other things which are very important to the human beings, going back to my initial idea, human signal processing. We're very sensitive to dynamics and to modulation. And for example, to separate speech from music or noise, there's much evidence to say that the human being exploits the dynamics of the speech signal to recognize it to be of interest or important, which is different to noise. Since the air conditioning or the heating noise is constant in this room, you really are not listening to it. But if you listen carefully, it's there, but it's stationary, so the brain decides it's not interesting, immediately removes this. And so the dynamics and the modulation are also an important way of touching signal. Mathematical statistics can also be calculated from signals or estimated from signals, and these turn out to be extremely helpful in developing signal processing algorithms. So joining together ideas of, this goes back to Fourier, time and frequency, spatial processing, maybe something on dynamics and modulation in a statistical framework. We can try to bring together the body of know-how, the capability, exploiting as many dimensions as possible to extract as much information as possible for these kinds of signals. And maybe eventually we can achieve something as good as humans do. So, exploring these now, time frequency, many people will be familiar with a spectrogram, which has time on the horizontal and frequency on the vertical axis. And the strength of the signal is shown by the heat of the color. So maybe white hot is strong energy here, very low, cold energy. And so, starting with a voice activity detector, trying to detect speech, you might try to do this using energy, only energy in the time domain. But if you add the spatial dimension, then you can sense the probability of speech in a certain direction. So if you're standing at a party and you hear speech coming from this direction, then you're tempted to turn to listen to see if it's an interesting conversation you would like to chat with these people. Equalization is very well known in audio. We try to adjust the frequency content of a signal. If we add the spatial dimension, we can now control the frequency response in a given direction. So the directivity or polar pattern of rendering or even of sensing devices. And eventually, when we put many of these things together, an important, very important task in audio and acoustic signal processing is noise reduction, and there are a few techniques which exploit these ideas, and introducing spatial dimensions as well is something that we may also see later in the demo. Moving on now to space and time examples, where we put the space-time processing together. This allows us to do wavefield rendering using loudspeaker arrays, and we'll again see some of this in the demo later. And also, for example, to do direction of arrival estimation in 3 dimensions using a spherical microphone array, where on the right you can see the azimuth and elevation estimates, where the solid line shows the target is moving and the dotted line shows the estimated direction in terms of azimuth and elevation of the target. So introducing space-time processing now allows us to determine the direction of a source not only in a plane but actually also in 3 dimensions. De-reverberation is also an important task for speech enhancement, for speech recognition, and in this case we build mathematical models which try to identify the acoustics of a room, identify the impulse response from the source to many microphones, including modeling of noise, and then having performed a system identification, pass this to an equalization algorithm which will modify the signals gathered by the microphones using a multi-channel processor to produce a dry signal from reverberant microphone signals. And this is a technology which is again advancing more in the last 5 years, still some way to go. But exploiting space-time processing, since it's very hard to do this with only one sensor, may be impossible. I mentioned statistics as an important tool for us to use, and we can study the statistics of speech signals, of noise signals, of all acoustic signals, and maybe we can separate out different sources. The air conditioning can be separated from the speech signal based on the statistical properties, perhaps independence or non-Gaussianity. And if we combine many aspects of statistical signal processing together, perhaps using the well-known Trinicon framework, then this allows us to do some very advanced signal processing, which in this experiment here, we have 5 people talking, but only 2 microphones. Classically, 2 microphones can only separate 2 sources, but using some additional statistical features, we can separate even up to 5 talkers with only 2 microphones. So I mentioned the practicalities of space-time processing, Mobile phone manufacturers normally have one microphone at a push. Maybe an expensive phone can have two. And even with two microphones, we can do some very significant space-time processing. So I'd like to move now to talk a little bit more about applications. And the first of those could be in the context of sensing, so space-time sensing. Imagine we have sound source localization or sound source tracking. And in the context of localization, of course, in the real world we have reverberation. We already saw some ideas how this may be processed. And noise. We already saw some ideas of how this might be processed. And the key applications here would be, for example, Skype TV. So I'm sure that many people would agree with me that Microsoft has launched a campaign on the home living room, trying to bring their technology into an entertainment context instead of only an office context, with the introduction of the Xbox 360 Connect system, which allows you to use your TV more or less as a computer and certainly for Skype-type communications. And then you have the problem that you're sitting on your sofa and the TV is at a distance of 4 meters, and somebody is making coffee in the kitchen, somebody is using the vacuum cleaner, and you want to have a good acoustic channel between the person talking on the sofa and the TV at 4 meters distance. So this is a good challenge for space-time processing, and the Xbox Connect system tries to do this by merging together also some clever image processing technology with some clever audio processing technology. And in terms of practicality, $99. So for $99, you can buy a huge step forward in space-time processing for acoustics. So it can be done if the volume is good to produce realistic products. Of course, then people may move during this scenario, and therefore it's great to be able to track the talkers and the sound sources. And of course, we have seen a development in telephony from original handheld telephony. Now we are feeling comfortable with hands-free telephony, particularly in cars. But what about chair-free voice interfaces? It means you can stand up from the sofa, you can walk around your living room and still continue to talk on a Skype TV conversation. I have another example where this might be useful in a, let's say, mobile office environment. Some colleagues are having a meeting with coffee or something, and they use, this is a webcam, but it could equally be a spherical microphone array. You have here glass windows, so you have many reflections. I'm sure there's some noise because it's not a private environment, and the people are themselves moving a little bit whilst they're talking and making other noises. So this is a really practical, testing, challenging environment for space-time processing, acquisition of audio signals. We have many stimulus, not only the office environment, many stimulus for this kind of work, maybe even in deep space. So now I'll show you something more light-hearted and humorous. So here we have the Star Trek example of hands-free communication. So the captain doesn't need to wear a headset in order to communicate with his ship or with his adversaries, the Klingons. He can simply talk, and probably in the arms of his chair, he has some microphone array signal processing. So this is definitely not science fiction. But of course, you can see that this technology is many years old, and the new generation, now not so clear on this picture, but now the captain can stand up and walk around the bridge of the Starship Enterprise, and his voice is still perfectly clear to the Klingons when he's having a conversation on the big screen monitor. So we can go from maybe 1970s or 80s to the 1990s, 2000s, where we have an improvement in space-time signal processing. So it's a humorous example, but underneath it there is some reality which can also take place in our real world. For example, this is an actual project, so this is not science fiction, this is fact, for an example of space-time communications in the new helmet for NASA missions. So we have a problem when you wear a spacesuit and you go outside of the vehicle. Inside the helmet is a boom microphone, and if the astronaut is working for several hours, maybe the boom microphone becomes not well aligned with the mouth. Maybe if he sneezes or somehow it gets distorted, then he has to come inside the ship, take off the helmet, reposition, put the helmet back, go outside the ship. He's already lost 1 or 2 hours. So a new technology is to put MEMS microphones, as shown here, into the helmet and to use array signal processing, space-time or acoustic signal processing inside the helmet. There's the advantage of redundancy. If one of them fails, it can still operate not too bad, and it can launch a beam of sensitivity towards the mouth of the astronaut, and it doesn't get in the way, and it doesn't have to be correctly aligned. It can be adaptively focused. So MEMS microphones like this, in combination with the mathematics of space-time signal processing, can lead to actually to real and futuristic emerging applications. Not only in sensing, but also in rendering. So rendering immersive audio to match or exceed what can be achieved with images. So we're familiar now to see 3D movies, but the sound, it's maybe surround sound, so you can hear sounds from behind, but we would like to be able to render exact sound fields, perhaps using contiguous arrays or virtual sources. And we'll see some examples of those also in the demos. Another nice application for sophisticated rendering would be zone-specific rendering, where you might have a different language at a different seat. So if we were able to have a space-time system in this room, if you would like to listen in German, then you could have loudspeakers give German over there, see some German speakers or Italian speakers. Or maybe in the back of your car, your kids may be watching different movies and they can hear the sound of the different movies without interference, and so the driver cannot hear it. So zone-specific rendering is also a good challenge. One of the techniques that may enable us to do that is wave-field rendering, and one of my partners has kindly supplied me with a video which I can show to illustrate this. So in this case we have the circular loudspeaker array, and we will try to generate the wavefront which is due to a virtual source outside of the circular array. And we can see as the acoustic waves build up during this simulation, it's slowed down, so we can see what's happening. We have the wavefront propagating through the circle, and if you stand inside the circle, you have a remarkably immersive experience because you receive actually a very clear and accurate representation of the wavefront. So one of the projects that we're talking about today, the SCENIC project, will be discussed in much more detail by Augusto Sarti in our next talk, but I wanted to give just a very brief preview to show the link from my talk into his talk. So in the SCENIC paradigm, we realize that we do space-time acoustic signal processing in real spaces. And this means that we have to somehow include the effect of the space. And the question is, should we try to be robust to the spatial effects? In other words, they don't mess with our algorithms, or should we try to exploit them and not work against the environment? And so the SCENIC paradigm is exploring the second approach, and basically aimed at analyzing, inferring, and exploiting the acoustic environment. So Augusto will talk some more about that shortly, but I wanted to bring some conclusions now. First of all, to say that growing our capability from single sensors to multiple sensors, or from single loudspeakers to multiple loudspeakers, opens the door to a new world in which we can do space-time signal processing, and that there are many opportunities of exploiting spatial information such that we can understand, and I put understand in quotation marks, something more like human beings do, so that we can understand these acoustic scenes and render synthetic acoustic scenes more accurately. And that the task becomes harder, so where are the new challenges for research in this area? The task becomes harder as we move to more complex environments. Right now we do pretty well if we have a shoebox room, simple rectangular room. What about more complex scenes that require more sources and more sensors to get control? Okay, so thank you for that. That's the end of my talk.